Wave-particle relationships. Okay, the thing that has become apparent to me is that we don't necessarily understand these equations as well as I hope that we did. These and other equations, which also leads me to what the final is probably going to be organized as. I'm probably going to have it be old school, like definition type things. Like I might even give you an equation and ask you, what is this variable? In fact, I'm toying with the idea of the entire test being that. You just described this. For example, things that really drive me nuts is when I see something like this, 2d sine theta equals m lambda, and someone throws the mass of an electron in there for m. It's just supposed to be an integer value, integrated. Not integrated, you want to use that word.
Isn't that the maximum?
True, you can help me out with this.
It's the number of distance.
No, yeah, a for loop. When you go through an end loop, you are
Now I need to. It's iterate.
Iterate. That's the word I could come up with. Thank you. It's just supposed to be an iteration. And in the event that the problem tells you that there's only one place that you have coherence, you know that this is m equals 1 right off the bat. That's what it would be. It's certainly not the mass of an electron. Yeah, if any of you guys, I should say if any of you guys, if some of you guys use units a little more, you would be able to tell that obviously that's not going to work out too well for you. This is in meters. This is in meters, and everything else is unitless. You also throw a mass in there, obviously it doesn't work out. All right, so let's go back and talk about these wave-particle relationships. Now, in this, problem example 4.3 that we went over in class, and question 1 on your exam, and question 3 on your exam, at some point we had to assume that kinetic energy of a particle, we're talking about a massive particle. Now, whenever the book uses the term massive particle, they're not saying it's gigantic. It's just literally a particle that has mass. So you have two types of particles, massive particles and massless particles. So don't think that it has to be giant anyway. All right, we said that the energy is equal to the kinetic energy, which is equal to 1/2 mv squared. And we run with that. And even at given times, we said, all right, well, this is kinetic energy, which could potentially be equal to electric potential energy if it passes through some sort of voltage. And we said that is equal to QV. And I've decided I'm going to do my voltages like this. So I'm going to kind of determine that. Underline it. I think that's going to be quite easier. Plus, I'm about to teach 2212 again next semester, so adopting that now. All right, so all of this is true for massive particles. The question is, how does this relate back to that stuff that we've got over there? Let's first look at the momentum. Momentum is equal to each wavelength like this. Isn't it that Danza Kudrow song that you don't like?
I just don't like it in why.
Is that one of the ones that goes through iterations? You ever have songs like that where you, oh, I like this, now I hate it.
Yeah.
And now I like it again, now I hate it.
Yeah.
I was trying to find a song that you didn't like so to play, because you got that soothing stuff in there. All right, momentum equals h lambda, and even in this example problem, we set this up as equally mass times velocity. Now, in doing so, we weren't explicit about this, but this right here is the classic relationship for a particle. So I'm going to be really specific about this, and I'm going to write this as mass v particle is equal to momentum is equal to h over lambda. Now, h is a constant, it's a Planck's constant, so we don't really have to concern ourselves. What about lambda? Is lambda ready to put a wave or a particle subscript on this? No, it's kind of silly. I mean, it's identifying both, but obviously it's identifying the wave-like properties of the object. This, I do have to put a subscript on it, because there's also the v of the wave, the velocity of the wave itself. So then what a lot of you guys wanted to do is you wanted to run and take the energy equation and say this is equal to HF. And then you say, well, I happen to know that frequency is equal to, this is 1 over seconds. So in that case, I must have V over lambda. And you simply wrote HV over lambda. Okay, this is not an incorrect relationship. But the problem is, we've seen this a bunch of times. Lambda times the frequency is equal to the velocity. The velocity of what? Wave. This is all from 2212 stuff. This is the wave. As is this. You can't just shove the velocity of the particle in here. It doesn't work out. Bad things happen. Bad things. Okay. And also, if we just looked at this, if I wrote this as E equals HF equals HV wave over lambda, if we get back over here, this looks to be to say that momentum times velocity, if that's true. So let's go ahead and see if this is in fact true, if this relation holds up. If we didn't know whether or not this was V wave or V particle. Let's start the classical relationship. First, energy. 1/2 mass velocity squared, assuming that it's kinetic energy. And then over here we've just got mass times velocity. We end up with this extra term. We see that that relationship doesn't work out. Okay, what about if we try this relativistically? Okay, maybe this energy I'm talking about includes the rest energy, because this is a particle of mass. So if that's the case, then I can rewrite this as gamma U mc squared, that's my total energy of a particle, kinetic and rest energy, is equal to gamma U times mu times U. Now this is only true if this is the case. This is only true if c squared is equal to u squared. And we're kind of okay with that. Because that's saying if we're moving at the speed of light, then energy equals PV. So that is to say that E equals PC. And we've already seen that. That is an equation for a massless particle. Okay. But for a massive particle, we know that this is the velocity of the wave. It has to be, because this doesn't work out here, and this is certainly not going to work out here for a massive particle, because we can't be moving the speed of light. So, yeah. All right, so let's get back here. Now, on this, when I say it's the wave-particle relationships, what I'm referring to is on the left-hand side, we have the particleness. So you can say, yeah, I'll just put particle on this side, and wave on this side. This is how the two relate to each other. On one side and then the other side. So on this side, I can set this equal to mass times velocity. And I can set this equal to 1/2 mass times velocity squared, assuming we're not moving relativistically. I can't, however, start manipulating the right side and expect to get results that make sense. Alright, so let's see if we can't relate, we can find a way to relate these two. So I'm going to give you guys some more equations that you will now have. I want to relate momentum and frequency, and I want to relate energy with wavelength. So I want yet another set of equations so that I can get this frequency up into here, and I get the wavelength down into energy. Well, let's just start off simply with momentum equals mass times velocity. Okay. I can rewrite this as 2m times 1/2 times mv squared. Look what I did there. Squared what's in there, so obviously I can go right back. I separated the m's, and then I have 2 and 1/2. So this would just go back to being m squared v squared, which is underneath there. Now, I have obvious reasons to want to do this. then I call this 2ME. And if that's the case, then I come down here and say that the momentum is equal to 2MHF, or P squared equals 2MHF. And I'll have a relationship that involves the mass of the particle, this M being mass, obviously, like bulk, obviously, Planck's constant, and the frequency. And we can relate those now. Again, don't substitute out frequency for velocity unit again, because we're looking at the velocity of the wave. All right, so what about E? What about energy? Energy. Energy can be written as 1/2 mv squared. And if you do the math on it, this is also just p squared over 2m. And if you guys ever take any more physics, you'll find out that this is classical the way that energy is written. You should talk to. All right, so p squared over 2m. Well, if that's the case, my p squared there is going to be equal to h squared over 2m lambda squared. And that's it. There's nothing complicated about this. And simply just write that one down, more or less. You don't look like you like that. Who? Jared. Jared just gave
Sounds like what come from?
They say furrowed brow. What part is?
Well, the two M's cancel.
Where?
Did you plug in what P squared is Q, right?
I didn't put. I'm sorry. I did not put this up here.
Oh, okay.
I suppose I could have. That could make life interesting. But then we'll, yeah, and then that. Well, watch what happens when we do
Back
that.
to where we started.
Yeah. We're
Yeah.
going to end up with 2m HF over 2m, which is just HF.
Yeah.
Not terribly interesting for
Yeah.
our goal cuts. But
That's all I thought you plugged in.
real. Yeah, no, I actually plugged in the
Yeah.
here. All right, so we want to keep in mind that this left side, and I guess I should have introduced it. The book's got a good part of this right after example 4.3, and it talks about where your particles are weighted, or where your velocity is away towards particle. But you can just divide it right down to half and think of left and right sides. Okay, so if you remember making that mistake, here we go.
Could you also explain in volts, because I missed out on the homework too, and I'm,
Sure.
for some reason,
I don't even want to look. I'm not looking right now. Or else you're just going to hit a stanchion shoot. You're going to hit a stanchion thing, right?
Yeah.
So I can just choose to look at my test rate later, right? I'd rather do that.
yeah.
No, I wouldn't.
I'm slightly okay with this. Did you get the high score again?
Don't even talk.
I thought I did that.
Darn it.
I didn't do that about
Where's the code here?
You can try it.
I grade all the problems independently too, so I grade 3 and I start from the back, and then grade 2 and grade 1. So I actually didn't even know it was moderately okay. But all right, so here's the solution guide. And we're going to go through them.
Oh, okay.
I was a little bit safe.
The one thing
Like a band-aid, just rip it off.
I do have to be careful what I tell you guys though. But I mean, you guys have an impressive the mode of transportation for conversation in this thing. I tell Nina one day, I said, by the way, you're the only one who got 1, and Kyle comes up to me the next day and says, by the way, I heard Nina's the only one who got number 1
I
right.
saw her.
How did that even happen?
I saw her in lab. She asked me how I did, and I was like, I feel like I did pretty good.
I didn't
I'm
ask
the only one
you,
that
you
got number
asked
1
me.
right. I'm like, so. Plus, there's like 6 people here. It's really not that hard.
Yeah.
It just smells like fire with you.
I mean, it's kind of like in my probability class, there were 7 of us.
From now on, I'm just going to send out lies and just see how far the lies go up.
You go pretty far right there.
You see this spread into your other classes?
Alright,
should
so
just- you have
let's
people
go through
from-
these, because that's all I've got for today, because I want to talk about this test, because we need to understand this. Alright, the first one. Yeah, we got.
Has there been a homework or test that I've done that I have not had at least one terrible rounding error? 'Cause I swear.
Probably not, but your rounding error, it's a good thing I knew what you did, because your rounding error gave you an entirely egregious result. Yeah, what do you got?
Yes, for the next one, I don't really care if we use the equations. You usually throw all the equations on a sheet ahead of time.
It's straight out of the book. Do you want to know how I made that equation sheet? I went through and I picked out every single
Oh,
equation
no,
that was
but I
in the
realized
example problem.
See, but I realized when I was apparently going through the problems in the book, because the problems are like, oh, hey, I'm doing example 3.3. Oh, the equations I need for this are right there. And then I apparently did my equations and went about it.
Alright, you know what? I'll go through and I'll make an equation sheet for chapter 5 right now. I'm just going to put all of them that are on a sheet, and who knows what I'll end up using.
That would actually make me happy, because then they're out of order.
Don't do it for David, or just do it for David.
Alright, anyway,
Same people.
let's talk about question 1. Now, this is the way I thought question 1 was going to go. Obviously, you guys understood this. Well, maybe.
Pretty sure I missed 11 points because I misread the question.
Oh, and then, yes, remind me to talk about electron volts and volts. Alright, so. So, we know that K max is equal to HF minus 5. This is what bugs me. This is the type of thing, if I had known about it, I would have put a vocab part on this. What the heck is phi?
Work function?
Yes, it's the work function of the metal. Half of you equated this to the kinetic energy of the electron. I don't know why. It just says, okay, we'll take this to be the energy. And that's what really bothered me. And some of you started calculating the energy for the photon instead of the electron. There aren't that many equations in this class, so it's really important to understand what everything is. Okay, here, photon. Here is our electron. Now, we do know now, because of the wave particle relationships, that yes, this can also describe the wave parts of a massive object, but for this purpose, this is just describing the energy of the photon. In any case, you could go through, and as some of you did, which I was happy to see, and you calculate what your phi is, and it's 3.04 electron volts. Yay! And you could go through and you could calculate a whole bunch of other things. Or you could simply realize the whole point of the problem was that the kinetic energy of the electron is simply related to the voltage you went through. And it works out to be QV equals just the 1/2 mv squared. And you simply solve for your V and you get 1.29 volts. Or watts. For my answer. I forgot the L looks like.
So,
Okay.
joules divided by joules is just volts.
Okay, that's what we're going to get to here in a second. Alright, now, so. Okay, we have potential energy, which we have Q multiplied by V. Alright, this gives us joules back. And this is just the charge of whatever the object that we're dealing with. In this case, if we're dealing with an electron, it's just one elementary charge. Okay, so we can have the conversion from joules to electron volts simply dividing this by this 1Q, the 1 electron volts, and then we have electron volts. The amount of energy, by definition, what an electron volt is, the amount of energy it takes an electron to travel through 1 volt. So, if the problem wants to know what the voltage is required to go through X amount of electron volts to get that much energy, it's X amount of volts. It's the exact same number. Now, that's only because an electron, it has a charge of 1 elementary charge. If you had something that had a higher charge, so let's say that I wanted, let's say I had a double electron, for argument's sake, and I say that I wanted it to have 50 electron volts of energy. What potential would it have to go through to get 50 electron volts of energy? Yeah, it would have to go through double. Because it's going to work that much harder to have to go through it because of its potential energy. Does that kind of make sense? So it's for the electron, they're the same. That's why
Yeah.
I basically smacked you on the head.
I had volts, and I was like, that doesn't seem right.
Just
And
hear my
then-
voice yelling at you.
a little E.
So
I
did
saw
mine.
that little E,
Mhm.
and I shouldn't have.
Oh, you actually added that in?
I had it as volts, I was like, that doesn't look right. And so then I sweet little E.
They're the same for electrons.
I was
Specifically for electrons, that's why it's called electron volts. Okay, so this first one, what I expected everyone to do is I expected everyone to kind of waste their time going through the first part and realize they didn't need any of that, and then to get down to the bottom and then just do the simple answer of that. That literally what's in dashes is all you had to write down for this problem. The problem is we got sidetracked hugely over understanding what kinetic energy was, what the work function was,
And turn anything to the fundamental charge.
what a fundamental charge is. Yeah, some really simple stuff, guys. So that makes me nervous.
So 12 on this, because I thought that was a little difficult.
All right, let's move on to question 2. Sorry for the coffee stains on question 2.
Well, let's see, what's there? The velocity. I know I got the velocity right. I just picked one number.
Yes, true.
So on the sheet, you said P equals P squared 2n.
Okay,
Divided by
go ahead,
2n.
go ahead, find this number.
P squared over 2n, yes.
So that means V equals P squared
Go
divided by
ahead, right now.
2n
I don't
cubed.
want right now.
I don't know why.
Just looking at it. Shouldn't it-
I'm pretty sure I missed the 11 points.
Yeah, I don't know why I wrote
I just wanted to make sure.
Yeah, hey guys, I got sloppy and I was in a hurry on this. The Q should be in the denominator in my results there. Okay. All right, and the second one, a couple of things that we had problems with. One, if we say that it differs by 1.5%, which one is going to be longer? How do you know? So this is a photon comes in, and there's a photon that comes out. So we'll talk about the incident photon and the exiting photon, two separate photons. If I say that they differ by 1.5%, which one has a longer wavelength, and how do you know? We got you.
Shouldn't the one that comes out be the larger?
Yes.
Because it's the incident minus the initial, and you need that to be positive. So
If nothing else, that's a perfectly fine way to go about it. Look at the equation and say, equation kind of tells me that the exiting wavelength has to be longer. And I'm kind of fine with that. That's using deductive reasoning.
also, I mean, isn't the energy of that lesser and thus
Exactly. The energy of a longer wavelength is necessarily lower. Energy and wavelength scale inversely. So the smaller the wavelength, the higher the energy. And this is why we even, where a lot of this quantum mechanics stuff even comes from, is the fact that when we start talking about tiny wavelengths, the energy gets high. It's the longer wavelengths where things start acting more like waves instead of particles. Okay, that was a problem. The other problem, I want to talk about this. Hey Kyle, I got a question for you. Okay, if I have $1 and I tell you to add 20% to that, what do you get? Okay, now I say take 20% off that, what do you get? Now what do you get?
Not a dollar.
It's not $1.
0.2 times 120.
Which is,
Well,
what's 10% of $1.20?
12 cents.
12 cents, so it's 2 of that.
so it would be
24 cents.
96.
96 cents. Point being is that 20% above versus 20% below is not the same thing. I didn't hurt you hard on that, but that is the one thing also we have to be careful. They differ by 1.5%. You have to have one of them being 1.015 and 1 versus you can't have one being 1 and the other being 0.095. It doesn't work that way. You can still say that those differ by 1.5%, but the idea being is that we're talking about the incident photon came in, and then the other one differed by 1.5%. If you actually take that 0.985, I need to change that. If you take that 0.985 and set that equal to 1, and see the difference between there, all of a sudden now that new photon is going to vary by more than 1.5%. It's like 1.65% or something like that. It's larger. The other thing is, you guys, okay, like simple things like reading the question. randomly chose, I don't know, I'll put 75 degrees here, or I'll put 120 degrees here, I don't really care. Come on, just read the damn question. Get the numbers right. Yeah, I like Gary did that. Yeah, I'm saying these things, but I honestly don't. That one I remember deeply, but the other one I didn't remember deeply. All right, so question 2 actually went really well. I'd say that one went the best. Question 3. This was the reason that we had the whole lecture that we did just now. This is also the one that I added the extra points. So the first two were 33, this one's 34. I did that kind of as a benefit. I would have liked question 3 to be more heavily weighted. That would have been a negative effect on your grades. Problems here range from the things that we were talking about before, not understanding where to get your velocity from, to simple geometry questions of how to draw a triangle, or you can't take a sine and cosine of 90 degrees, that doesn't work. To also understanding what the incident angle that you had to use. So this whole thing with these Bragg guys is it's the angle incident to the plane of incidence, which in this case was 65 degrees. So I didn't kill anybody if they missed that, but that was a really important part, is understanding what angle goes into the equation. The reason that this stuff matters so much to me is because, again, we're not in 2201 or 2211 anymore. I want to know that you understand the things you're plugging in. It bugs me when just random throwing numbers into stuff. I think that's pretty self-explanatory, so you can go through my solution here. I wrote it out in over detail. My original one was smaller, so you did. Overall, the grades were much higher than last time. I think the grades almost were to a B- average. So, pretty good. Yeah, I guess that's it. On Tuesday, we'll start in earnest on Chapter 5. So, do you guys have any questions about what stuff on there? I really recommend that you try to go back through them, because I'm going to hit all these topics on the final too. So, if you have questions, I'd be happy to work through any of these.
Well, I'll have questions for you on Monday.
Yeah, same here. I gotta go study for the Eagle test.
Like, see, I gotta look at everything in detail and then questions.
All right, so have a good weekend, guys.
Still need my book.
No, you good.
Actually, no, I had a question not related to this, not really related to this class though.
What's that?
Okay, me and Cody were having a discussion, years ago, whenever we talked about was it 50 years that passed?
Wait, what?
Okay, we were arguing about Snow with Interstellar in the fact of the black hole. Did they say 50 years is going to pass until they got really close to it? 50 years
Sounds right, but I don't know.
Okay. How you they didn't give any sort of background?
No, they did. They talked about the number of years that was going to happen. They said, I think that they did. The bigger, have you guys seen Interstellar? In fact, I'm glad you brought that up.
Oh, yeah.
You
I've
didn't
seen
see
the
it?
trailer. I didn't see the movie.
I really recommend you guys go see this movie. It directly relates to the stuff that we did here in general relativity. And it's neat because they handle it reasonably well. Go see it. Go see it. It was a phenomenal movie. Oh, yeah. Yeah, it was a really, really good movie. And it does, I've never seen a movie actually even attempt to discuss general relativity. And they do it, and they do it really well. And it's awesome. It's a good movie. You liked it, didn't you?
Yeah.
Cody liked it. So there you go. Go see it.
Watch it.
Okay.